Welcome to The Explainer. Today, we're diving into 10 absolutely mind-bending scientific anomalies in nature. We are going to look at things that fundamentally challenge how we understand reality itself. So, we're going to visualize some of the most fascinating, frankly bizarre behaviors in the universe, just to try and make sense of what seems completely impossible. Get ready, because what we're about to see literally breaks the boundaries of everyday logic. So think about the classical rules of physics we all learned back in school. You know the drill. A ball rolls down a hill, objects have a fixed measurable location, and time marches firmly and predictably in one single direction, right? But what if the universe is quietly breaking its own rules right in front of you? Because when we look closer, down at the quantum level, the comfortable reality we rely on just completely unravels. Everything you thought you knew gets turned upside down. Okay, let's dive into this. Section 1. Biology's hidden quantum engines, the microscopic world inside living things. We normally think of quantum weirdness as something that only happens in multi-million-dollar supercooled laboratories. But actually, it's happening right in the leaves on the trees and the birds right outside your window.
Let's start with our first paradox, the mystery of quantum biology. And we'll begin with a seemingly impossible number, 99%. Back in 2007, Professor Graham Fleming's research team at UC Berkeley was looking at energy transfer in photosynthetic proteins, and they found that plants were converting solar energy with an efficiency reaching about 95 to 99%. I mean, that is approaching absolute perfection. To pull this off, the energy wasn't just taking a single path, like a pinball bouncing down a machine. No, it was existing simultaneously across multiple pathways, a phenomenon we call quantum coherence. The energy essentially smells out the most efficient route by taking all possible routes at exactly the same time. Now here's why that is absolutely staggering. Standard physics tells us that quantum coherence should be incredibly fragile. In a warm, wet, chaotic biological environment, like a leaf baking in the summer sun at 37 degrees Celsius, this coherence should collapse in literally a quadrillionth of a second. The background noise of the environment should just destroy it instantly. But it doesn't. And it's not just plants doing this. European robins are using quantum entanglement in their retinas to physically see and navigate the Earth's weak magnetic field when they migrate. And our very own enzymes? They use quantum tunneling to teleport particles right through solid barriers, which accelerates our biochemical reactions by millions of times. These biological systems are somehow maintaining these delicate quantum states in warm, messy environments and completely defying our classical expectations of how nature is supposed to work.
And that brings us to our second paradox, which was framed just brilliantly by physicist Jeremy England in 2015. He demonstrated mathematically that atoms, when they are subjected to a sustained energy source like heat or sunlight, will automatically reorganize themselves to dissipate that energy more efficiently. Under this thermodynamic framework, life isn't some miraculous one-off exception to the rules of the universe. No, self-replication is just an optimal strategy for generating entropy. Think about how crazy that is for a second. Your consciousness, your curiosity, your very existence. It's a thermodynamic inevitability. You are nature's most efficient way of dispersing energy. At a fundamental level, you are essentially no different from a condensing snowflake or a swirling tornado.
Section 2. The strange power of observation. How watching changes the world. Now, what's really interesting about this slide is the idea that the mere act of looking at something actually alters reality itself.
To understand our third paradox, let's look at a really deceptive, conceptual question that was posed by physicists Avshalom Elitzur and Lev Vaidman back in 1993. The question is, does detecting an object necessarily require disturbing it? In our everyday, classical physics reality, the answer is an absolute, unquestionable yes. You see a chair because light physically bounces off it and hits your eye. If there's no interaction, no light hitting the object, you get zero information. But the quantum world has a totally different answer, and it honestly feels a bit like magic.
In 1994, a team led by Paul Kwiat at Los Alamos National Laboratory put this exact question to the test. They set up an interferometer where a single photon's path was split into two separate branches, and the shocking result? They could detect the presence of a physical object blocking one of the paths without a single photon actually touching the object. They eventually achieved an accuracy rate of over 85% with absolutely zero physical contact. The mere presence of the object fundamentally altered the outcome at the detector. This proved we can gather information about reality without any energy or signal passing back and forth. Just pause and think about what that implies. The universe allows us to look at something, to know it is there, without ever touching it with a single particle of light.
And observation doesn't just detect things, it influences time itself, which leads to our fourth paradox. You might have actually heard of the quantum Zeno effect, where watching a system continuously actually freezes it in place, stopping its decay. It's essentially the quantum version of the old saying, "A watched pot never boils." But physicist Savrio Pascasio showed that if you tune the frequency of your observation pulses to a very specific, hyper-short window, you trigger the quantum anti-Zeno effect. So instead of freezing the system, your observation actively forces it to decompose, change states, or decay significantly faster. The universe doesn't just tick along at a fixed pace in the background. How fast a biological or physical system breaks down can literally depend on how frequently it is being watched.
Section 3. Breaking reality and mathematics, when fundamental laws fail. We are about to break the most basic mathematical laws you rely on every single day. So the crucial point is to let go of what you think is intuitively obvious about physical objects.
For our fifth paradox, let's look at the 2013 quantum Cheshire-Cat experiment. Researchers fired a neutron through an interferometer, placing it in this delicate superposition across two completely different paths. Astonishingly, the physical neutron itself went down one path, while its magnetic moment, which is its inherent defining property, went down the other path. To ground this in reality, imagine the chair you are sitting on right now. Theoretically, the physical mass of your chair could be separated entirely from its color or its shape. At the fundamental level, an object and its defining essence are not securely bound together. Nature can actually pull them apart, much like the smile of the Cheshire Cat lingering after the cat itself has completely vanished.
Now, if that wasn't strange enough, our sixth paradox breaks down basic counting. The classic pigeonhole principle is something a toddler intuitively understands, right? If you put 3 objects into 2 boxes, at least one box absolutely must contain 2 objects. It's an undeniable law of logic and math. And yet, in 2016, Yakir Aharonov and his team proved this completely fails in the quantum realm. Using what they call weak measurement techniques, they placed 3 quantum particles into 2 distinct boxes. The result? 0 overlap. No 2 particles shared a single box. When you measure reality gently enough, particles can somehow occupy the same finite space without ever sharing the same local position. The fundamental math of basic counting just completely breaks down.
Section 4. The existential blind spot. The limits of human perception. We're going to look at the terrifying limitations of what we can genuinely know about the world around us. And this brilliantly illustrates just how much of reality is deeply hidden from our everyday view.
This brings us to paradox number 7. For decades, scientists argued about the true nature of the quantum wave function. Was it a real, tangible, physical thing, or was it just a convenient mathematical tool representing our own human ignorance of a system? Well, in 2011, the PBR theorem proved mathematically that the wave function must represent a real, objective physical state. What this means for you is absolutely profound. It means the table right in front of you doesn't just exist in the ordinary, solid way you think it does. It truly exists in a bizarre state of probability superposition, a literal wave of potential until a measurement or interaction forces it to collapse into the solid object you can touch and feel.
But our blind spots aren't just quantum, they are existential, which leads to our 8th paradox. In 2010, researchers at the Future of Humanity Institute identified a terrifying concept called the anthropic shadow. When we calculate the historical risks of apocalyptic events, things like massive asteroid impacts, gamma-ray bursts, or global pandemics, our data contains an absolute unavoidable survival bias. Why? Because the civilizations or species that were wiped out by a massive catastrophe aren't around to record it in the history books. Our entire historical sample, literally every data point we have, is completely filtered through the lens of our own survival. The true frequency of world-ending disasters in nature could be vastly higher than our best mathematical models predict, simply because extinct observers cannot share their data.
Section 5. Rewriting history and time, the illusion of a linear past. Prepare to question the one-way flow of time itself. Let's move to and see how this builds into our final, most mind-bending paradoxes yet.
For our 9th paradox, we look at how things settle over time. Classically, if you want to reach a destination, starting closer means you get there first. It just makes sense, right? But in 2019, physicist Adolfo Del Campo predicted the quantum Mpemba effect. It turns out, a quantum system prepared in a state farther away from equilibrium can actually reach its baseline much faster than a system starting closer. It's kind of like a hot cup of water freezing faster than a lukewarm cup, but scaled down to the fabric of reality itself.
A system's historical trajectory, the complex, turbulent path it took to get to its current state, actually shapes its future behavior far more than its present immediate state does. It defies literally everything we experience in our daily lives about how systems slow down and settle.
But it gets even wilder with our 10th and final paradox. In 1999, physicist Yoon Ho Kim conducted the now famous quantum eraser experiment. This split entangled photons into two paths. The signal photon hit a detector first, firmly recording a specific interference pattern. It was an event that happened, objectively, in the past. Later, the researchers erased the path information of its entangled partner photon in the future. Miraculously, the action of erasing information in the future somehow reached backward in time and completely rewrote the physical pattern the first photon had already made in the past. It literally changed history.
The implications of this are just staggering. The trace was formed on the detector, the event was seemingly over, and yet its state was utterly transformed by an operation occurring later in time. We've seen how biology uses quantum engines, how observation literally shapes reality, how fundamental math collapses, and how time itself is not a one-way street. So I want to leave you with this single, powerful thought. If the past can truly be altered by an event in the future, how many truths are awaiting a decision never made?